Hello, welcome to the another lecture of control system and instrumentation. I am Mr. Prajit from Asansol Engineering College. Like to giving you some ideas about analogous system. Already I discussed from lecture 1 to lecture 5 respectively what is control system, what are the types of control system, especially that is open loop and closed loop control system, and what are the types of feedback, that is negative feedback, positive feedback system, and what is the exact definition of transfer function, how to determine transfer function based on block diagram reduction rules and signal flow graph based on Mason's gains formula. That things are also analyzed, and besides I mentioned how to determine transfer function for electrical circuit as well as electromechanical appliances. Now this ensuing discussion will be going on how can we represent the theme is how can we represent an electrical system in an equivalent mechanical way, or vice versa, that is how can I represent a mechanical system in an equivalent electrical circuit nature. That's why I am telling that is known as the analogous system. So before proceeding further, we should have a sufficient knowledge regarding the basic physics about that. Here see, modeling of translational mechanical system. Translational mechanical systems move along a straight line, and these systems mainly consist of three basic elements. Those are mass, spring and dashpot or damper. And if a force is applied to a translational mechanical system, then it is opposed by opposing force due to mass, elasticity and friction of the system. Since the applied force and the opposing forces are in opposite directions, obviously the algebraic sum of the forces acting on the system is 0. Let us now see the force opposed by these three elements individually. At first I will discuss about mass, then spring, then dashpot or damper respectively. So mass is the property of a body which stores kinetic energy. See, according to the right hand side diagram, m is denoted by mass, f is the exerted force, correspondingly small x is the respective displacement of the given mass. So if a force is applied on a body having mass m, then it is opposed by an opposing force due to mass. This opposing force is proportional to the acceleration of the body. Obviously it comes from the formula of Newton's second law. And assume elasticity and friction are negligible, where F is the applied force, m is mass, a is acceleration, x is displacement, F suffix m is the opposing force due to mass. Then we can write as F suffix x is directly proportional to a stands for acceleration, or we can write as after removing the variation symbol, we can write F suffix m is equal to m into m is the mass. Okay, that is constant obviously. So acceleration is nothing, that is rate of change of velocity with respect to time. That's why see, if in terms of displacement we can written as F suffix m is equal to m into d2x dt square, or we can write F suffix m is equal to mx double dot. X double dot stands for second order derivative. Now spring is that element which stores potential energy. Yes, so these fundamental knowledges should be known to you people, and already you have studied in basic physics. And if a force is applied, see on the right hand side diagram, if a force is applied on spring K, then it is opposed by an opposing force due to elasticity of spring. This opposing force is proportional to the displacement of the spring, and assume mass and friction are negligible. Here if I am telling F is the applied force, F suffix K is the opposing force due to elasticity of spring, K is the spring constant, X is the displacement. That's why we can write as the F should be directly proportional to X. So we can again write as F suffix K is equal to K into X, because K is my spring constant or variation constant in this scenario. So it can be rewritten as F is equal to K, F suffix K is equal to K into X. Now when I am speaking regarding the dashpot or damper, if a force is applied on a dashpot B, then it is opposed by an opposing force due to friction of the dashpot. This opposing force is proportional to the velocity of the body. Yes, that's important. Assume mass and elasticity are negligible, where F suffix B is the opposing force due to friction of dashpot, B is the frictional coefficient, V is the velocity, X is displacement. So F suffix B is directly proportional to V, or we can rewrite as F suffix B is equal to B into V. B is the frictional coefficient and V is the velocity, that is rate of change of displacement with respect to time. That's why we can rewrite as F suffix B is equal to capital B into dx by dt, or we can write as equal to B into x single dot. X single dot stands for first order derivative. Okay. Now, modeling of rotational mechanical system. So previously I discussed about translational mechanical system. In this scenario, see moment of inertia, torsional spring and dashpot, again it will come into the consideration. So rotational mechanical systems move about a fixed axis. Obviously, these systems mainly consist of three basic elements. Those are moment of inertia. Purposingly we are denoting by moment of inertia J, torsional spring and dashpot. So if a torque is applied to a rotational mechanical system, then it is opposed by opposing torques due to moment of inertia, elasticity and friction of the system. Since the applied torque and the opposing torques are in opposite directions, the algebraic sum of torques acting on the system is 0. Let us now see the torque opposed by these three elements individually. Just like as translational mechanical system, again we will do individual performance of moment of inertia, torsional spring and dashpot respectively. Okay. Here see, in translational mechanical system, mass stores kinetic energy. Similarly, in rotational mechanical system, moment of inertia stores kinetic energy. If a torque is applied on a body having moment of inertia J, then it is opposed by an opposing torque due to the moment of inertia, and this opposing torque is proportional to angular acceleration of the body. Assume elasticity and friction are negligible. Where see, according to the right hand side diagram, see, if I am looking that is the diagram where J is highlighted, that is the cylindrical shaft, you can speak. The area of cross section should be, that is depending on the cylinder. J is the moment of inertia, T is the torque and theta stands for angular displacement. So here see, T is the applied torque, T suffix J is the opposing torque due to moment of inertia, and J is the moment of inertia, alpha is the angular acceleration, yes, and theta is the angular displacement. So from the concept of dynamics, we can rewrite as T suffix J, that is torque due to the opposing torque due to the moment of inertia. T suffix J is directly proportional to alpha, that is angular acceleration, or we can write, after omitting the variation symbol, T suffix J is equal to J into alpha, that is J into d2 theta by dt square, that is theta double dot. Rate of that is angular acceleration is nothing, that is rate of change of angular velocity with respect to time. Now, so T is equal to T suffix J is equal to J into theta double dot, because that is theta double dot is nothing, that is second order derivative. Now, torsional spring. In translational mechanical system, spring stores potential energy. Similarly, in a rotational mechanical system, torsional spring also stores potential energy. If a torque is applied on torsional spring K, then it is opposed by an opposing torque due to the elasticity of torsional spring. This opposing torque is proportional to the angular displacement of the torsional spring. Assume that the moment of inertia and friction are negligible. So from the right hand side diagram, we can rewrite as T suffix K is directly proportional to theta, implies T suffix K is equal to K into theta, or T is equal to T suffix K is equal to K into theta. Obviously, where T is the applied torque, T suffix K is the opposing torque due to elasticity of torsional spring, and K is the torsional spring constant, theta is the angular displacement. Now, dashpot. If a torque is applied on dashpot B, then it is opposed by an opposing torque due to the rotational friction of the dashpot. This opposing torque is proportional to the angular velocity of the body. Assume that the moment of inertia and elasticity are negligible. That's why we can rewrite as T suffix B is directly proportional to the angular velocity omega. So again we can rewrite as T suffix B is equal to B into omega, omega is nothing that is rate of change of this angular displacement with respect to time, that is t suffix b is equal to b into d theta by dt, or we can write as b into theta dot. Okay, now t is equal to t suffix b is equal to b into d theta by dt, that is due to the presence of dash pot, that balancing torque equation. So that should be in your mind. So here capital B is the rotational friction coefficient, omega is the angular velocity, and theta is the angular displacement. Now our concerning title is coming. Before coming on to this chapter, obviously we should have a sufficient knowledge regarding those fundamental things, otherwise it will be a little bit tough. See, analogous system. Two systems are said to be analogous to each other if the following two conditions are satisfied. Number one, the two systems are physically different. Number two, differential equation modeling of these two systems are same. Yes, that is the another key point. Differential equation modeling of these two systems are same. Electrical systems and mechanical systems are two physically different systems. There are two types of electrical analogies of translational mechanical systems. Those are force voltage analogy, can be denoted by FV analogy, and force current analogy. And in for FV analogy, that is force voltage analogy, the mathematical equations of translational mechanical system are compared with mesh equations of the electrical system. Here, force voltage analogy. See, on the right hand side diagram is valid for mechanical system. Here see the mass is highlighted, denoted by M, B is the damper or dashpot, K is the spring constant, and F is the exerted force, and correspondingly small x is the respective displacement of the mass, that is mass spring balance system. So for that system, that is the translational mechanical system is highlighted on the given figure. So we can write from the concept of previous discussions, the force balanced equation for the system is due to the individual forces should be summed. That means individual forces means I am speaking force due to the mass M, force due to the damper B, force due to the spring constant K. So it will be force balance equation for this system will be F is equal to F suffix M plus F suffix B plus F suffix K. So it will be F suffix M is M into d2x by dt square plus B into dx by dt plus K into x, and that is denoted by 1. And consider the following electrical system as shown in the figure. These circuits consist of a resistor, an inductor, and a capacitor, obviously RLC series combination below diagram. And all these electrical elements are connected in series. The input voltage applied to this circuit is V volts, and the current flowing through the circuit is I amp. Okay, now all of we know mesh equation. For that we can write as V is equal to R into I plus L di dt plus 1 by C integral I into dt. Now we know what is the definition of current, that is the rate of change of charge with respect to time. So we are substituting I is equal to dq by dt. So after substitution I is equal to dq by dt to the equation 2, it generates V is equal to R into dq by dt plus L into d2q by dt square plus q by c plus q by c. Okay, so again we can rewrite the above one, that is V is equal to L into d2q by dt square plus R into dq by dt plus 1 by c into q. So it is a second order differential equation for a variable q, that is charge. Keep in your mind. Now comparing equation 1 and 3 respectively. 1 is also the second order differential equation with variable x. Then one system is valid for mechanical equation, equation 3 is valid for electrical equation. Now we will tally all these 1 and 3 equation to generate the analogous system. So we will get the analogous quantities of the translational mechanical system and electrical system. The following tables are, if we are comparing each with, so force F, obviously here if I am considering the left hand side force is tallied with the voltage for electrical system. Mass M into d2x dt square should be tallied with L into d2q by dt square. So M is tallied compared with L. Inductance. Friction coefficient B should be compared with resistance R. Spring constant K should be compared with the reciprocal of the capacitance 1 by C. Displacement X should be compared with charge Q. Velocity V should be compared with the current I. So these tables should be on your mind to evaluate the respective equivalent diagram. Otherwise you have to evaluate with the help of the mathematical analysis. Okay, this is valid for force voltage analogy system. Now for torque voltage, that is for rotational mechanical system, we are not at all disturbing this voltage equation 3. Just for rotational mechanical system, what thing we are doing, see, in this analogy, the torque voltage analogy, the mathematical equations of rotational mechanical system are compared with mesh equations of the electrical system. So rotational mechanical system is comprised of the balancing torque equation due to the individual components. That means total torque equation T is equal to torque due to the presence of moment of inertia, that is T suffix j, plus due to the presence of damping constant, or that is the dashpot T suffix b, plus the torsional spring constant T suffix k. So collectively we can rewrite as T is equal to j into theta double dot plus b theta dot plus k theta. Theta double dot means j into d2 theta by dt square plus b into d theta by dt plus k theta. This is equation number 4. Then you have to compare this equation 4. This is my rotational mechanical system with the electrical equation 3, because all the order are remaining same. 3 is also second order differential equation, 4 is also second order differential equation. So for torque voltage analogy we can write as T, torque, should be tallied with the voltage V for the left hand side variable. Now moment of inertia J should be compared with the inductance L. Rotational frictional coefficient B should be compared with the resistance R. Then torsional spring constant K should be varied with your 1 by C, reciprocal of the capacitance. Angular displacement theta is compared with the charge Q, and angular velocity omega should be compared with the current I. So torque voltage relationship is established. Okay, now we are focusing to the force current analogy. Obviously previously we considered about RLC series combination. In case of force current analogy we will construct RLC in parallel combination. So in force current analogy, see, for the translation mechanical system, with the nodal equations of the electrical system can be highlighted as, here we will construct the resistor, inductor and capacitor in a parallel nature. So obviously from the right hand side diagram we can establish the nodal equation will be the total current I should be equal to V by R plus 1 by L integral of V dt plus C into dV by dt. That is equation number 5. Now see, we have to substitute V is equal to d psi by dt. Psi is nothing, that is flux. So psi is flux. That's why we have to generate again the second order differential equation by which we can compare the equation 1 with this element. Okay, so when we will substitute about V is equal to d psi by dt on equation 5, it generates the I is equal to 1 by R into d psi by dt plus 1 by L into psi plus C into d2 psi by dt square. Again rearranging the above one, we can generate I is equal to C into d2 psi by dt square plus 1 by R d psi by dt plus 1 by L into psi. So again see, we are constructing equation 6 is a second order differential equation with a variable psi. Then again you can compare this equation 6 with the equation 1 for the force current analogy. So obviously see, that is the due to the presence of variable x, that is in terms of second order differential equation, here the variable is psi, flux. So here when I am constructing force current analogy, similarly we can write, you can compare in same way. Force is equivalently represented as current, mass m is equivalently represented as capacitance, frictional coefficient can be rewritten as B, can be written as reciprocal of resistance, that is 1 by R, conductance. Spring constant K is nothing, reciprocal of inductance 1 by L. Displacement X is nothing, that is magnetic flux psi. And velocity V can be represented as voltage V. Similarly, for torque current analogy, already my current equation is established. So my current equation is established. Then we will compare this equation with 4. So equation 4 and 6 should be compared with each other, by which we can generate torque current C. For the rotational mechanical system, torque can be equivalent represented as current. Moment of inertia J can be equivalent represented as capacitance, because this is the capacitance, that is I is equal to C into d2 psi by dt square plus 1 by r d psi dt plus 1 by L into psi C. When I am looking to the equation 4, that is also C. T is equal to J into d2 theta by dt square plus B into d theta by dt plus k theta. So J, moment of inertia, should be equivalently represented as capacitance. Now see here, that is moment of inertia is equivalently represented as capacitance C. Rotational frictional coefficient B can be represented as the reciprocal of the resistance 1 by R. Torsional spring constant K can be represented as the reciprocal of the inductance 1 by L. Angular displacement theta, magnetic flux, angular velocity omega is voltage V. These are the respective assignment. How can we establish an analogy between force voltage and force current concept, and how can we establish an analogy between torque voltage and torque current? So these are the respective things, and these are the respective references. I already told you people, I am taking help from these books, and that's all for today. Okay.